Lesson 4.2, Conservation of Momentum. A system. A system is all the objects involved in the problem. For momentum, that means the things that are going to crash into each other. What is crashing? Usually it's only two objects that crash at a time. Now when they crash, there are two types of forces. Internal forces, which are the forces the objects exert on each other, like when two cars crash, they apply forces on each other. And external forces, forces exerted by things outside the system, like if there's a strong wind blowing the cars around. That would be external. Consider two balls that hit each other in the air. During the collision, there are internal forces. The force from ball 1 onto ball 2, and the force from ball 2 onto ball 1. There's also external forces, which are their weights. If I take the impulse momentum theorem, the forces from object 1 are its weight and the force of the other ball hitting it. That equals its change in momentum. Object 2 is the same thing, its weight and the other ball hitting it times time equals its change in momentum. If I distribute the t and add these, I get that, which are all the forces times t. Then the final momentums minus the initial momentums. So this is the external forces plus the internal forces times t equals our change in momentum. Since force of the first ball on the second one and the second ball on the first one are equal and opposite, the sum of the internal forces is 0. So that leaves us with just the external forces times time equals our change in momentum. But if it's an isolated system, which means there's no external forces, we'll have 0 equals our change in momentum, or our initial momentum equals our final momentum. That is the law of conservation of momentum. It says in an isolated system, the total momentum remains constant. So P0, our initial momentum, equals PF, our final momentum. And these are the total momentums of all the objects in the system. Your system can contain any number of objects. Our reasoning strategy is to first of all decide on the system. Which objects are actually involved in our collision? And then you identify the internal and external forces. Is your system isolated? If not, then you cannot use the conservation of momentum. But if it is isolated, you set the total initial momentum of the isolated system equal to the total final momentum. Two billiard balls are colliding on a table. In order to apply the law of conservation of momentum, what should the system be? One ball or both? Well, what's hitting each other? Both of them. So it has to be both billiard balls. Our external forces are the weight and the normal force. Assuming the table is horizontal, these are going to cancel each other out. If it were only one ball that we called our system, the force of the second ball hitting it would not cancel with anything, and we would have some external force. So our system has to be both balls, so the forces of them hitting are internal forces and cancel out. A hockey puck of mass 0.17 kilograms and velocity of 5 meters per second is caught by a 0.5 kilogram mitten laying on the ice. What is the combined velocity after the puck is in the mitten? Well, initially we have the puck, and it's moving. It has a velocity of 5 meters per second. It's moving towards a mitten, and its initial velocity is 0. Then they hit, and the puck is in the mitten, going at some unknown velocity. Well, our system is just the puck and the mitten. So is it isolated? Yeah, it says ignore friction, so there's no outside forces. So we have the puck and then the initial velocity of the puck. We have the mitten and the initial velocity of the mitten. That should equal the final momentum of the puck plus the final momentum of the mitten. So our mass of the puck, 0.17, and its initial velocity is 5. The mass of the mitten is 0.5, and its initial velocity is 0. Mass of the puck, its final velocity. I don't know what that is. That's what we're looking for. And the mitten, but the mitten has the same final velocity. So the puck and the mitten have the same final velocity. So the total initial momentum is 0.85 kilogram meters per second. Since these are like terms, I can just add 0.67 kilograms times the final velocity, divide, and the combined final velocity is 1.27 meters per second. So notice the puck hit the mitten and they stayed together and it slowed down. It slowed down because there was more mass. A 5 kilogram pitching machine is placed on some frictionless ice. It shoots a .15 kilogram baseball horizontally at 35 meters per second. How fast is the pitching machine moving after it shoots the ball? It's moving. Why should it be moving? Well, I don't know. Our system is the ball and the machine. So we have the ball, initial velocity of the ball, plus the machine, the initial velocity of the machine, equals the ball, final velocity of the ball, the machine, final velocity of the machine. So the mass of the ball is 0.15 kilograms, and its initial velocity is 0 because it hasn't been shot yet. The mass of the machine is 5 kilograms, and its initial velocity is 0. It's sitting still, waiting to shoot the ball. The mass of the ball is 0.15 kilograms. Its final velocity, it says, is 35 meters per second. The mass of the machine is 5 kilograms, and we're looking for its final velocity. So 0 equals 5.25 kilogram meters per second. Subtract the 5.25 kilogram meters per second and divide by 5. When I divide by 5, I get negative 1.05 meters per second. What's that mean? That means it's going backwards at 1.5 meters per second. It shot the ball forwards, so the thing shooting the ball goes backwards. That is why you feel a recoil when you shoot a gun. The bullet gets thrown forward, so the gun gets thrown backwards.